Today's lecture is about linear probing. We've been considering dictionaries, which are simple data structures that store key-value pairs. In Python, they're provided as a primitive, and in Java, they're a standard interface. We already had two approaches to making dictionaries. The first is to make a large data structure that fits the entire universe. The other is to make a search tree, which has log n time per operation and linear space overall. And the question was, can we get the best of both worlds? Can we get O1 time per operation and O in space overall? We first considered a special case where the keys are selected uniformly at random from the entire universe. We considered the strategy of allocating a smaller array of size m and storing each key ki in the slot ki mod m. If multiple items ended up in the same spot, then we concatenate them in a linked list. So each key gets mapped to ki mod m. We showed that the expected length of any list was n over m, and that the maximum length of all the lists was log m plus log n over log m minus log n with probability at least 1 minus 1 over n. The only tools we used was linearity of expectation and the union bound. The homework asked you to refine some of these bounds. Returning to our question of how to make a dictionary competitive with both arrays and search trees, we've shown that for random keys, for any epsilon greater than 0, we can get space n to the 1 plus epsilon and expected time 1 over epsilon. Our general interest is in adversarially placed keys, not uniformly at random. The big idea is to introduce randomness and randomly re-index the keys into another large universe U so that the re-indexed keys looked as if they were selected uniformly at random from the universe. The overall scheme maps a key ki to hki mod m for a hash function h. A hash function is a function that is fast to evaluate, but the output effectively looks random. Some examples of hash functions include SHA-2 or the .hashcode method provided in Java. The net effect is a uniformly random mapping from the set of keys to the set of indices 1 through m. That said, the assumption that we have a perfect, truly random hash function is not practical either. So we looked more carefully at the notion of an ideal hash function. In our max load analysis, total independence was used in particular to show that the probability of all of k balls going into a particular bin was 1 over m to the k. If you don't have perfect independence, it wasn't hard to come up with an example where each item can get sent to a certain hash slot uniformly at random, and yet the maximum load is always the worst case of n. That said, total independence was too much to ask for basic information theoretic reasons. To recap, independence is good for load balancing, but perfect independence is impractical. So are there other, perhaps weaker notions of independence that we can use instead? So we introduced some weaker notions of independence. We considered universal hash functions, pairwise independent hash functions, pairwise independent and uniform hash functions, three-wise independent hash functions, four-wise independent hash functions, and more generally, k-wise independent hash functions. And then we asked two questions: can we construct such functions efficiently, and are these functions even useful? We considered universal hash functions and considered in particular the function h of x is equal to ax plus b mod p, where p was a large prime bigger than m, and a and b were selected uniformly at random. Schematically, it can be drawn like this. We showed that this simple hash function was in fact universal. And then we analyzed its performance for hash tables. We observed that the expected time of a lookup for a key k was proportional to the load at the slot where it gets hashed into, which was equal to the number of collisions of other keys with that key k. In turn, we showed that the expected number of collisions with key k was n minus 1 over m. Here we used linearity of expectation, and then we got the 1 over m out of the universality of the hash function. We thus get the theorem that the expected time for each operation was big O n over m. While the expected time per operation was something like big O n over m, it did not give us a stronger bound like being able to bound the maximum load with any degree of confidence. So what could we say instead? We showed that the probability that the number of collisions exceeds the expectation by a factor of 10 was at most 1 over 10, and the probability that the number of collisions exceeded the expectation by a factor of 100 was at most 1 over 100, and then for a factor of 1,000, at most 1 over 1,000. And these all followed from what's called Markov's inequality. We switch over to a new part of the lecture. Sadly, over the weekend when I was making these slides, my Apple Pencil actually broke. So instead I had to type up these notes, and instead we're going to go through this note together. We start with Kwise independence. Recall that a collection of n variables is Kwise independent if for any k of the variables, any fixed k values y1 through yk, the probability that the first variable is equal to y1 and the second variable is equal to y2 all the way through to the kth variable equal to yk is equal to the probability that the first variable is equal to the first value multiplied and taken apart from the probability that the second item is equal to the second value apart from the others, all multiplied all the way through by the probability that the kth variable is equal to the kth value. Lemma. Let x1 through xk be Kwise independent random variables. Then the expected value of x1 times x2 times x3 all the way up to xk is equal to the expected value of x1 times the expected value of x2 times all the way through to the expected value of xk. That is, the expected value of the product of the xk's is equal to the product of the expected value of the xi's. Before proving lemma 1.1, consider the following simple example. Let x1 through xk be 0, 1 random variables where each xi denotes the outcome of a fair coin toss, 0 for tails and 1 for heads. Then x1 through xk is equal to 1 if and only if all of the coin tosses come up heads and 0 otherwise. Consider the following parallel universes. Suppose each xi was based on a different independent coin toss. That is, x1 through xk are mutually independent. Then the probability that k independent coin tosses all comes up heads is 1 over 2 to the k, so the expected value of x1 times x2 all the way through xk is equal to 1 over 2 to the k. On the other hand, suppose each xi was based on the same coin toss. That is, x1 is equal to x2, which is equal to x3, all the way on to xk. They certainly are not independent. Then the probability that all of x1 through xk is equal to 1 is the probability of a single coin coming up heads, 1/2. And so the expected value of the product, x1 times x2 up to xk, is equal to 1/2. In particular, there's an exponential gap between independent and non-independent coin tosses. Let's prove the lemma. The expected value of x1 times x2 times all the way to xk is equal to the sum over all possible values y1 through yk of the product of the y's, y1 times y2 up to yk, times the probability that x1 is equal to y1, x2 is equal to y2, and so on forth down to xk is equal to yk. This is exactly the definition of expectation. By Kwise independence, we can take that probability and write it as a product of individual probabilities. So now we have probability of x1 is equal to y1 all alone times the probability that x2 is equal to y2 all alone times all the way on down to the probability that xk is equal to yk, again taken apart from the others. From here, we can now regroup the sum by variable. So we have the sum over all values y1, that the probability of x1 is equal to y1 times y sub 1, and then the same sum for y2 and x2 all the way down to the sum for yk and xk. Finally, each sum by itself is the expected value of the corresponding variable, which completes the proof. Now we will state and prove a concentration inequality for 4 Kwise independent random variables. Let x1 through xn be 0, 1 indicator variables that are 4 Kwise independent, where for each I, the expected value of xi is equal to p. Let mu denote the average, which is equal to pn, which is the expected value of the sum of xi's. Then, for any beta greater than mu, we claim that the probability that the sum is greater than or equal to beta is at most mu plus 3 times mu squared divided by beta minus mu to the fourth. For example, if you take beta is equal to, say, 2 times the average, then the right-hand side becomes the average plus 3 times the average squared divided by the average to the fourth. And if mu is at least, say, 1, then the right-hand side roughly becomes 4 divided by the average squared. This is much better than, for example, Markov's inequality, where a probability of being greater than or equal to 2 times the average was at most 1/2. Proof. We have that the probability that the sum of xi's is greater than or equal to beta is equal to the probability that the sum minus the average is greater than or equal to beta minus the average. And here's the surprising step. We're going to take the fourth power of either side and say that the probability of the sum minus the average to the fourth is greater than or equal to beta minus the average to the fourth. And then we apply a Markov's inequality to the non-negative random variable, the sum minus the average to the fourth, and get that the probability is less than or equal to the expected value of the sum minus the average to the fourth divided by beta minus the average to the fourth. We claim that this expectation, the expected value of the sum minus the average to the fourth, is at most the average plus 3 times the average squared. This would complete the proof. We first have that the expected value of the sum minus the average to the fourth is equal to expected value of the sum of xi minus p, all taken to the fourth, because the average is equal to p times n. Now, the sum of xi minus p taken to the fourth expands out to the sum of I equals 1 to n xi minus p to the fourth plus 4 choose 2 summing all over coordinates I less than j xi minus p squared times xj minus p squared plus a bunch of monomials that have at least one xi minus p term with degree 1. Some examples of monomials in the third category would be x1 minus p cubed times x2 minus p, or x1 minus p squared times x2 minus p times x3 minus p, or x1 minus p times x2 minus p times x3 minus p times x4 minus p. Now, consider the expected value of each of these categories of monomials. For the first category, for each I, we have that the expected value of xi minus p to the fourth is equal to, because xi is equal to 1 with probability p times 1 minus p to the fourth, plus, because xi is equal to 0 with probability 1 minus p times p to the fourth, and this is less than or equal to p times 1 minus p. For the second category, given two indices I not equal to j, we have that the expected value of xi minus p squared times xj minus p squared is equal to, and here we use pairwise independence, the expected value of xi minus p squared times the expected value of xj minus p squared. And all of this is less than or equal to p squared times 1 minus p squared, because the expected value of xi minus p squared is equal to p times 1 minus p squared plus 1 minus p times p squared, which is less than or equal to p times 1 minus p. Each monomial in the third category has expected value 0. This is because we can pull out the degree 1 term by independence, which by itself has expected value 0. For example, the expected value of x1 minus p1 cubed times x2 minus p2 is equal to the expected value of x1 minus p1 cubed times the expected value of x2 minus p2 by pairwise independence, and expected value of x2 minus p2 is equal to 0. Plugging back in, we now have the expected value of the sum minus the average to the fourth is equal to np times 1 minus p plus n choose 2 from times 4 choose 2 p squared times 1 minus p squared, which is less than or equal to np plus 3 times np squared. That's the average plus 3 times the average squared, which is exactly what we were going for. Remark, the claim would hold even if the variables xi were not identically distributed with the same probability of being equal to 1 of p. As long as they are fourwise independent and each of them were in the range 0 to 1, the same conclusion would hold. The restricted setting is enough for the applications ahead and simplify the presentation. We can go back to the hash table data structures from before and consider what would happen if we use a fourwise independent hash function rather than the universal hash function we used last time. Theorem. Suppose we throw n balls into n bins, where each ball goes into a bin uniformly at random, and the distribution of balls into bins is 4-wise independent. Then for any fixed probability of error between 0 and 1, delta, the max load is at most big O n to the 1/4 divided by delta to the 1/4, with probably at least 1 minus delta. We leave the proof as a homework exercise. Linear probing. All of the hashing schemes studied so far have handled collisions in basically the same way. If multiple items land in the same slot, then we made a linked list out of all the items hashed to that slot. In the homework, we considered a variant where rather than a list, we made another hash table for each slot. In either case, we made a secondary data structure for each slot with multiple items. Here we will try something new and arguably more natural. If a key finds its hash slot already occupied, find another empty slot in the array and put it there instead. The new hash table, like before, consists of an array A1 through M and a hash function H from the set 1 to U to the set 1 to M. To insert an item X, we first place X at A h of X. If A h of X is already occupied, then we instead find the next unoccupied index in the array and place h of X there instead. If we reach the end of the array A, then we wrap around to A1. Since items X do not necessarily get stored at their hash cell A h of X, we carefully use the following terminology. We say that an item hashes to a cell A of I if h of X is equal to I. We say that item X occupies a cell AI if AI is equal to X. We stress that an item X hashing into a cell AI does not imply that X occupies AI, and that an item X occupying a cell AI does not imply that X hashes to AI. Given two indices A and B in 1 through M, we define the interval from A to B, denoted A comma B, to be the set of indices A, A plus 1, and so on up to M mod M. The mod M means that if B is less than A, then we wrap around. The interval from I to B is a set A, A plus 1, all the way up to M, and then starting over from 1, 2, 3, on to B. One might imagine the array A arranged in a circle rather than a line. Lemma. If an item X occupies cell L out of M, then all of the cells in the interval Hx to L are occupied. Proof. The invariant holds initially with an empty array. We maintain the invariant in the lemma with each insertion as we insert X in the next unoccupied cell starting from H of X. Lemma 2.1 justifies the following lookup procedure. To look up an item X, we first check entry A h of X. If item X is not there and the slot is empty, then we conclude the item is not in the array. If the slot A h of X is occupied, but occupied by some item other than X, then we start scanning the array cells to the right of A of h of X for either item X or an empty cell. If we find an empty slot before finding X, then by lemma 2.1, it must be that X is not in the hash table. To delete an item X, we first find it by the same process as when looking up. Starting from A h of X, we start scanning the cells until we find X. When we find X at some cell I, we delete X from the cell, but then to restore the invariant in lemma 2.1, we look for another item to try to fill it. In particular, we start scanning the cells for the first item X1 with its hash code HX1 less than equal to I1, or else an empty cell. If we find such an item X1 in a cell I1, then we put it in the cell I where X was deleted from. We then continue scanning for an item to replace I1, and so forth. This hashing scheme is called linear probing, and has a special place in the history of computer science. It was analyzed by Donald Knuth in 1964. Knuth is sometimes called the father of the analysis of algorithms, and he is credited with formalizing the subject and popularizing big O notation. As Knuth tells it, this was the first algorithm he ever formally analyzed, and therefore, arguably, the first algorithm that anyone has ever so formally analyzed. He showed that for ideal hash functions, the expected time of any operation is big O n over m minus n all squared. In particular, a constant whenever m is bigger than n by a constant factor. This data structure also works very well in practice, even if hash functions in practice are not truly independent. Part of that is owed to the simplicity of the data structure. Scanning an array is extremely fast on hardware, and much faster than chasing pointers along a linked list. Post-Knuth, there remained a question of how much independence was required to get constant running time and expectation. Around 1990, Schmidt and Siegel showed that about log n wise independence sufficed. Then, in 2007, Pog and Rutzik showed that just 5 wise independence sufficed. This is dramatic progress for arguably the oldest problem in algorithm design. Soon after, it was shown that 4 wise independence was not enough, so the answer is 5. Here we give a simplified analysis of the result of Pog and Rutzik. We don't put too much emphasis on the constants, preferring to keep the main ideas as clear as possible. Much better constants can be found in the original paper, and also the reader is encouraged to refine the analysis themselves. Other proofs of the constant time bound can be found in the attached resources. Theorem: for m greater than or equal to 8n, linear probing takes expected constant time per operation. Proof: each operation on an item x takes time proportional to the number of consecutive occupied cells starting from a h of x. To help analyze its length, we introduce the notion of runs. A run is defined as a maximal interval of occupied slots. Every occupied cell is contained in a unique run. If an item x is in the hash table, then a h of x is occupied, and x occupies a cell in the run containing a h of x. Each operation with an item x takes time at most proportional to the length of the run containing x. Let I equals h of x, and let r be the run at index I. Note that r and its length, size of r, are random. The expected running time up to constants is the expected value of the length of r, which is equal to the sum of L equals 1 to n, L times the probability that the length is exactly equal to L. So this is exactly the definition of expectation. And then we're going to bucket these lengths by factors of 2. So we sum over k from 1 to log n, 2 to the k times the probability that the length of the run is between 2 to the k minus 1 exclusive and 2 to the k inclusive. For each natural number k, let I sub k be the interval of length 2 to the k plus 1 minus 1, centered at I, ranging from I minus 2 to the k minus 1 to I plus 2 to the k minus 1. Here I've drawn the interval I sub k for the first few values of k. If r has length less than 2 to the k and contains I, then r must be contained in the interval I sub k plus 1. Moreover, if r has length greater than 2 to the k minus 1, then at least 2 to the k minus 1 items other than x hash to r. Thus, for each k, we have that the probability that the length of the run is between 2 to the k minus 1 and 2 to the k is at most the probability that 2 to the k minus 1 other items also hash into I sub k. Since h is 5-wise independent, conditional on hx equal to I, the remaining hash values are 4-wise independent, and each lands in I sub k with probability p, which is equal to the size of the interval ik divided by m. We have that the probability that the number of other items hashing into the interval I sub k being greater than 2 to the k minus 1 is at most, by the fourth order method from up above, 4 times the max of the average or the average squared divided by 2 to the k minus 1 minus the average to the fourth. This, in turn, because the average is at most 2 to the k minus 2, is at most 4 times 2 to the k minus 2 squared divided by 2 to the k minus 2 to the fourth. And that, when we cancel out all the powers of 2, is at most 1 over 2 to the 2k minus 6. Plugging back into the right-hand side above, we have that the expected running time up to constants is at most the right-hand side we had above, which is at most the sum, as k goes from 1 to log n, of 2 to the k times the upper bound we just got, 1 over 2 to the 2k minus 6. This is equal to 2 to the 6 times the sum as k goes from 1 to log n of 1 over 2 to the k, which is at most 2 to the 6. In particular, a constant.